Well, hi everyone. In this video, I'm going to outline a few of the very basic strategies that are used to count arrangements of objects. It turns out that there are a variety of different techniques that can be used in order to do that. And they come under the heading of 4 basic counting principles, and they align with the 4 basic arithmetic rules that we all know about, which are addition, subtraction, multiplication, and division. I would like to talk about counting strategies that are aligned to those 4 fundamental operations. Let me start with the addition principle. The addition principle is based around the following idea. That you have a set that is partitioned into non-overlapping, non-empty subsets whose union is the entire set S. Let me draw a little picture to kind of give you the flavor of this. Suppose that I have a set S here, but suppose that S is partitioned, which just means that it's decomposed into these non-overlapping subsets. Let's say S1, S2, S3, and so on, up to, let's say, SM. We have a bunch of different subsets that don't overlap with each other, but collectively, their union is the entire set S. Then what we can say is that the size of S, if we wanted to count how many elements are in S, what we could do is simply add up how many elements belong to each of the subsets within this partition. So we could find the size of S1, the size of S2, the size of S3. We could do all of those calculations separately and then add the results. Now, why would we use this principle? Well, maybe it's easier to count the number of ways of doing whatever is in S1 and the number of ways of doing whatever is in S2. In other words, counting the sets S1, S2, and so on separately might be easier than trying to think about the entire big set, capital S, of all possible arrangements at face value. Now, this is kind of the idea behind this addition principle. Let me write it out in words as well so that we can kind of have an idea what I'm talking about, and then we'll look at an example. So to complete a task, I would like to imagine that I have a task to complete and that there are several steps or several, let's say it differently, several different methods that we could use to complete this task, right? Suppose that, for example, method number 1, whatever that happens to be, method number 1 can be carried out or completed in N1 ways. So one possible method for completing the task might be what I'm calling method 1, and maybe there's N1 ways to do the task using that method. But maybe there's an alternative method, let's say method number 2, that can be completed, I'll use a ditto symbol here, in N2 ways, and so on and so on and so on. And maybe we go all the way down to method, let's say M, which can be completed in N sub M ways. Right? So then what the addition principle says is that if we have several methods to choose from, and we know how many ways we could carry out each of those methods individually, then the punchline of this addition principle is that there are N1 plus N2 plus N3 and so on up to NM ways to do the task. Okay. By now, you've maybe made the connection that method 1 is being represented in my picture over here by S1. S1 is the set of all of the ways of completing the task using method 1. S2 is the collection of all ways of completing the task using method 2, and so on and so on. So that essentially, the equation that I've written mathematically here at the bottom of this board is reflected in the addition principle as the total number of ways to do this task. Let's write down an example to sort of see how this would work in a real problem. Let's suppose that the task before us is to choose a dessert that we would like to have after our meal. And let's suppose that for dessert, let's suppose that we can choose, or we can have, ice cream or a shake. Can't have both, unfortunately, have to choose one. Either ice cream or a shake. And let's suppose there are 3 flavors of ice cream. So if you need to, you can imagine what flavors you might think of: vanilla, chocolate, strawberry, something like that. 3 flavors of ice cream and 4 flavors of shakes. Again, might be something you're thinking of already. Could be cookies and cream, vanilla, chocolate, strawberry, whatever, right? So there's 4 flavors of shakes. The question is, how many desserts are possible? In other words, how many choices do I have for the dessert that I would like to have after my dinner? So the idea here is that I can probably figure out this answer immediately. I can either have chocolate ice cream, vanilla ice cream, strawberry ice cream, or cookies and cream shake, vanilla shake, chocolate shake, or strawberry shake, right? So I'm choosing either one of the 3 flavors of ice cream or one of the 4 flavors of shakes. And so I have 2 methods that I can use to choose my dessert, right? One method is I can choose ice cream. And how many ways are there to choose ice cream? There's 3 ways, because there are 3 flavors of ice cream. Or the second method of choosing a dessert is to choose a shake. And because there are 4 flavors of shakes, I would have 4 ways of choosing my dessert using a shake. In other words, N1 is 3 and N2 is 4. Let's just write this down. We don't have a big solution here. We don't need a big solution. It's simply 2 possible desserts, right? They're mutually exclusive. We can't choose both. We have to pick either the ice cream or the shake. And so by the addition principle, we simply add these together and we get N1 plus N2 equals 7 possible desserts. Okay, so this is the situation where we have one task to complete and there's multiple different ways of completing that task. And we just simply add them all up. Basically what we have to do here. This is the addition principle. And this is what we would apply, for example, when we have a problem like this, where there's a task that we have more than one choice. So there's an or here. We're choosing ice cream or a shake, choosing just one of those, and together creating a single completion of that task. Now, this is very different than if the question said something like, how many ways can you choose an ice cream and a shake? Now you've got 3 choices for ice cream, 4 choices for a shake, and you get to pick one of each. So that's actually going to be not the addition principle, but the next thing I want to talk about, which is the multiplication principle. Because here, if I was asking how many ways are there to choose an ice cream and a shake, I actually have 2 tasks to do. And they are independent of one another. And I got 3 ways to do the first task, 4 ways to do the second task. And now, instead of adding them together, I would be multiplying the choices. So let's move on to talk about the multiplication principle for a moment. Sometimes what's a little bit challenging about this section is deciding which principle we're talking about. This word "or" right here is really critical for the addition principle. Okay, we have some mutually exclusive choices. We're only choosing one of those options. So we use the addition principle. But suppose here that we have, let's say, k tasks, not just one task, but k tasks. And if the ith task can be completed in n sub I ways, then there are n1 times n2 times ... times n sub m. Sorry, I said there were k tasks. So up to n sub k ways to complete all of the tasks. Right? In this case, that would be the number of ways. So again, as a sort of a follow-up example to our first example over here, the number of ways to choose an ice cream and a shake. So notice I've changed the "or" to an "and." If I'm choosing an ice cream and a shake, this is going to be n1 times n2. In other words, 3 times 4, which is 12 ways. So you could mix and match, figure out every combination, right? Either chocolate, vanilla, or strawberry ice cream paired with either cookies and cream, vanilla, chocolate, or strawberry shake. And I can multiply 3 times 4 and come up with 12 different combinations there. Okay. Just as another sort of more abstract example of this multiplication principle. The multiplication principle comes up a lot. You don't always realize that you are doing k tasks to solve a problem. For example, if I ask you, what is the number of 3-letter strings? You're actually, so we're talking about just strings of 3 characters. There's 26 letters in the alphabet, right? We have to think of this as 3 tasks. There's the task of choosing the first character, there's the task of choosing the second character, and there's the task of choosing the third character, right? We can actually think of it as 3 slots, and we can label each slot with how many choices there are, how many ways there are to complete each of those tasks of filling in each of those 3 slots. And because there are 26 letters in the alphabet and we have been given no other constraints, there would be 26 ways to do each of the individual tasks. But I have to use the multiplication principle now, which gives me 26 cubed ways to actually complete the 3-letter string. So the answer here would just be 26 cubed. Okay. Hopefully that makes a little bit of sense so far. So that's the multiplication principle. Let me take a moment. I'll come back over here. We have the addition principle and the multiplication principle so far. The addition principle is when there are several cases of which we're only going to choose one. several ways to complete one task. We can think of it as breaking it into cases, and each case can be counted separately and give us the total number of ways of completing the task by adding up the number of ways of doing each case. Right? That's different from the multiplication principle, where we actually have several steps in the process to completing one task that has several parts to it. And we have to complete each part sort of independently of each other part. Okay, so that's the multiplication principle and the addition principle. Now, the subtraction principle is the one I want to talk about next. And this is a very simple idea, which is just that sometimes, I'll call this number 3, the subtraction principle. Sometimes it's easier to count what you don't want, how many ways there are to do the opposite of what you actually wanted to count, and subtract from some sort of a universal total, right? So let's just make that as a sort of a generic note here. Sometimes it is easier to count what you don't want, right? And subtract from some kind of a universal total. So as an example of that, suppose I ask you, how many 3-letter strings include a repeated letter? So I'm still making strings with 3 letters each, but I would like to figure out how many of these strings have some letter repeated. So for example, it could be, ABA would be an example because the letter A has been repeated. Or XXX would be another one because the X is being repeated, okay? It's a little bit tricky to directly count this. But if we instead ask ourselves, well, how many 3-letter strings do not have a repeated letter? That is suddenly a much easier question to answer, right? So the solution, and this is going to be done by what I'll call subtraction, is to say that we're going to take the total number of strings of 3 letters, which we just calculated in the previous example, right? Which is 26 cubed. So this is some sort of what I would call a universal total, the total number of strings of 3 letters. And I'm going to subtract what I don't want, which is that I don't want strings without repeated letters. Well, how many strings do not have any repeated letters? See, that's a little bit easier to actually count. I have 3 tasks again, right? I can use the multiplication principle. The first task has 26 possible letters to choose. But now, if I don't want to repeat the same letter again, then the second task is left with only 25 ways of being completed, because I have to pick a different letter than I did in the first slot. And now the third slot, I have 2 letters that I have to rule out, leaving me with only 24 choices, 24 ways to fill out the third letter. And so in fact, that is exactly the right amount to subtract off in coming up with our answer. So the answer would literally just be this difference right here. What we have right here are, that we're subtracting, are 3-letter strings with no repeats. with no repeats whatsoever, right? So that would be a nice way to do the problem. It is possible to do it directly. We'll learn about that with some more advanced techniques later on. But it's much easier in this case to solve this problem by using the subtraction principle. We count what we didn't want to keep track of and subtract it from some kind of a universal total. Okay. Maybe I can give you a slightly more involved example of the subtraction trick. I think this might be interesting as well. Let's take one more example. Come over here to write this one down. So another example of the subtraction trick would be something along these lines. How many strings of 7 digits this time, we'll take strings with 7 digits, contain at least 2 4s? How many strings of 7 digits contain at least 2 4s? Now, if I think about this, the total number of such strings of 7 digits, right? So the total, that's an easy thing, right? The total number of strings of 7 digits, of course, when I think about digits, I'm talking about the numbers 0 through 9. And I'm imagining that I can use any of those digits in any position, right? So in other words, again, by the multiplication principle, I have really 7 tasks to fill out here. I have to choose the first digit, choose the second digit, choose the third digit, and so on. Each of those choices can be fulfilled in 10 ways. Choose the first digit, 10 ways to do that. Choose the second digit, 10 ways to do that, and so on. So you're getting 10 choices, 10 choices, 10 choices for each one of those 7 tasks. By the multiplication principle, we would get 10 to the 7th ways of doing that. That's my universal total, the total number of 7-digit strings. But I want to now take away however many strings fail to have at least 2 4s. So that would be sort of my question now, if I'm going to use the subtraction trick, is how many such strings fail to have at least 2 4s. In other words, I would like to count strings of 7 digits that have either 0 4s or 1 4. Either no 4s at all or exactly 1 4. If you think about it, those are 2 mutually exclusive types of strings. A string that doesn't have any 4s can't be the same as some other string that has exactly 1 4. So I'm actually going to use the addition principle to answer this question. I'm going to figure out how many strings have no 4s in them. Then I'm going to figure out how many strings have exactly 1 4 in them. And then I'm going to add those together. So 7-digit strings with no 4s. If you want to think about these guys, feel free to pause the video. And, these are questions that we have the tools to answer already. It's perfectly reasonable to do that. And then you can always continue and see if you're concluding the same values that I am. Well, if I'm looking at 7-digit strings that don't have any 4s in them, doesn't that just mean that instead of 10 different digits, 10 different ways to choose a digit for each of the 7 slots, that I actually only have 9 digits available? I can't use the 4, but I can use any of the other digits, and that goes for all 7 slots of the string. 9 choices, 9 choices, 9 choices. So it's actually a multiplication principle going on right there. Okay. What about 7-digit strings with exactly 1 4? Again, feel free to pause. Think about it for yourself for a moment. Well, so I have to have exactly 1 4 in the string. So one of the choices, one of the tasks in building this string is to choose where is that 4 among the 7 slots. I have 7 choices for where I put that 4. Okay. If you need to, visualize it with a picture of 7 slots. I have 7 different places where the 1 4 that I have in my string could be. Maybe it goes right here. But that's a choice I have to make. I have 7 choices for where I'm going to put that 4. That leaves me with 6 other slots. And in each of those 6 other slots, I cannot use a 4. Which means I have what? 9 other digits available. 9 other digits available for each of those remaining 6 slots. Okay, so this is a multiplication principle again in this little subtask of creating 7-digit strings with exactly 1 4. So how many strings fail to have at least 2 4s? By the addition principle, it is simply 9 to the 7 plus 7 times 9 to the 6th. And that is what we actually want to subtract from the total number of 7-digit strings. And so the final answer to the problem by the subtraction trick, by the subtraction principle, would simply be 10 to the 7 minus this quantity of 9 to the 7 plus 7 times 9 to the 6th. We can get a calculator to simplify that answer if we wanted to. However, I almost think it's better to leave it like this, because when you leave it like this, it's easier, it's more transparent for somebody to understand where these numbers came from and how you were thinking through the counting process here. Okay, so I actually like when we have answers that are not simplified. Of course, it would make sense to get out a calculator and see if this is some kind of a reasonable number. But like it shouldn't come out negative, for example. But still, leaving the answer in this form, I think is a great idea. So there are a couple of examples of the subtraction principle. Count what you don't want and subtract it from some sort of universal total. Okay, hopefully everything is good with this. So we've talked about the addition principle, the multiplication principle, the subtraction principle, and so I have one more to go over with you, which is the division principle. The division principle is one that we're not going to do as much with, at least at this point in the course, but I at least want to add it to the notes now because we've been talking about the other arithmetic principles related to counting. But let's at least get this one written down. Number 4, the division principle. Just for the record here. And what this one says basically is that if we start with a finite set, let's call it S again. Let S be a finite set partitioned. We're going to, once again, like we did with the addition principle, we are going to partition the set S into K equal-sized parts. So I want to imagine that we can chop up the set S into parts that are all the same size. And let's suppose that there are K such parts, right? So then basically the question here is, can we figure out what K is? Right? Namely, then K can be determined from the following formula. We take the full size of the whole set S. Let's suppose that we know how to do that. We take the entire set S and we divide by the number of objects in one part. So that might be something relatively easier to calculate. If we focus just on one of the parts, right, then we can actually figure out how many different parts there are. So as an example of this, just taking this one kind of straight out of the textbook, but let's suppose that there are 740 pigeons in a collection of pigeonholes. So there's a total of 740 pigeons that are split among a variety of pigeonholes. Let's suppose now that if each pigeonhole holds 5 pigeons, then we could actually count how many pigeonholes that we have. So then the number of pigeonholes is simply obtained by taking the total number of pigeons. So we imagine these 740 pigeons, right? And we're placing them into various groups of 5, right? If we do that, then we can figure out how many groups we have, which is just another way of figuring out the number of pigeonholes. And that would be 740 divided by 5. So there would be, if we were counting how many pigeonholes are there, it would just simply be 148 in this case. So it's kind of a straightforward idea here. Sometimes the way that this gets applied is, okay, you have a number of objects that are all distinguishable from each other to begin with, but then somehow you want to divide out by the fact that actually they in some way look the same as each other. When they look the same as each other, then we shouldn't count them as being different. And so by dividing out by the sort of the degree to which these originally distinguishable objects are actually the same, we can then count how many objects we have in reality if we don't keep track of those sort of duplicates, so to speak. So we're going to use this idea quite a bit. For now, I just wanted to state it in a very simplistic form. This is the division principle. So we have the addition, multiplication, subtraction, and division principles. We've kind of looked at least 1 or 2 examples of each of those types. For sure, the most important ones are the subtraction principle and the multiplication principle. We're going to see those a lot. I think the addition principle is also very important, but fundamentally, counting the sizes of the subsets within the partition is where the hard work really comes into the addition principle. At the end of the day, you just have to add up a bunch of cases essentially in order to apply that rule. So, well, I hope that this has been useful. I hope that you've enjoyed this overview of 4 of the main techniques of counting. Sort of the natural next step that we're going to look at as we move forward now is how do we handle whether the objects that we are counting are repeated or not repeated. Kind of looked at an example of that already. And then also whether the order matters or doesn't matter. So we can end up with a variety of types of problems depending on just the fundamental answers to those 2 questions. Does the order matter? And is repetition allowed when we're counting arrangements of our objects? So I'll look forward to sharing that with you guys in the near future. But for now, thank you so much for your attention on this video. I look forward to seeing you all again very soon. Thanks a lot. Bye-bye.